Welcome to this video. And here we're gonna do inference review. This is our 6th review session for AP Stats final review. First, take a look at this diagram. We have population parameter, which separate out to two branches, mean mu and proportion p. For the mean, we have these three types of test. One sample, matched pairs, and two samples. For one sample, it will be one sample t or z test. Remember, if the question gives you a data, most likely it will be a z-test. Matched pairs will have one sample t-test for difference. That's the only case for matched pairs t-test. For two samples, it will be two sample t or z-test. For proportion p, it has two branches, one sample and two sample. For one sample, we have one sample z-test. For two samples, we have two sample z-test. So remember, when dealing with proportions, we only have z-test to choose. While for mean, it can be either t-test or z-test. Okay. So testing the relationship between two categorical variables, we're going to use Chi's test of independence. While testing the relationship between two quantitative variables, we're using t-test for the slope of the regression line. So notice the difference here. The biggest difference is categorical versus quantitative. Chi test is always with categorical, while the test for slope, t-test for slope, will always be quantitative. And here is a chart that kind of summarizes everything again and some additional requirements. For the means, we have those amount of situations. One sample z, we have to check those conditions. First, data is known, population is normal, or n is greater than 30, SRS. For two sample z, both data are known, both populations are normal, or both n's greater than 30. Both are SRS. One sample t, data is not known, SRS. Population is normal, or n is greater than 40, or n is between 15 and 40, and little skewness and no outliers, or n is less than 15 and no skewness and no outliers. So basically, the more sample size, the larger sample size you have, the more tolerance you can have on your graph. For matched pair t, we have to be sure that this is matched data. The list of differences has n greater than 40, or n between 15 and 40, and little skewness and no outliers, or n is less than 15 and no skewness and no outliers. Notice degrees of freedom is number of differences minus 1. Two sample t, we have to check is this independent SRS. Data are not known. Both populations are normal, or both n greater than 40, or n between 15 and 40 and little skewness and no outliers, or n less than 15, no skewness and no outliers. Degrees of freedom from calculator. For proportions, we have two situations, one sample z and two sample z. For one sample z, checking condition for SRS, NP greater than 10 and NQ greater than 10. Population at least 10 times n, or in other words, the sample that we're taking has to be less than 10% of the total population. For two sample z, make sure independent SRS, confidence interval, both N1P1 greater than or equal to 10, N1Q1 greater than or equal to 10, and same thing for second sample. When dealing with test, however, both N1P hat should be greater than or equal to 10, and N1Q hat should be greater than or equal to 10. Same thing for second sample, where p hat is the pooled proportion. And this is the only situation that we're going to use pooled proportion. Anywhere else, we don't use it. Both populations are 10x. Categorical variables, we only have chi-square. So chi-square goodness of fit and chi-square test of independence or homogeneity. For goodness of fit, one variable, working with counts, all expected value should be greater than 5, or all expected value greater than 1, and 80% of E is greater than 5. Degrees of freedom equal to numbers of categories minus 1. For test of independence or homogeneity, we have two categorical variables. We're working with counts. all E should be greater than 5 or all E greater than 1 and 80% of E greater than 5. Degrees of freedom is rho minus 1 times column minus 1. For the slope, we have t-test for the slope of the regression line, the only test that we have for slope. Checking for residual plot shows no pattern, curved, or fan with equal number of points above and below the x-axis. We want completely randomness for residual plot. Also, residual box plot shows little skewness and no outliers. We are tolerant for little skewness. Degrees of freedom is n minus 2. So notice the difference here. And here is another table. Sorry, not showing like the whole picture right here. Yeah, but basically like this is another hypothesis test review, showing you different conditions, like what formulas you should use. And I will see if I can post another PDF sometime in comments, but this is basically everything you need to know. Feel free to ask me if you really want a PDF version of this. Confidence interval review. Steps for performing any confidence interval. We're gonna name first name of confidence interval, second state assumptions or conditions, third give confidence interval, and fourth conclusion in context. These are the 4 main steps we've been doing over and over again in this unit, right? Inference. Not this unit, but just every chapter related to it. So confidence interval for one proportion, the assumptions are SRS, 10% rule, NP greater than 10, NQ greater than 10. Formula we're using is right here, p hat plus or minus z star times square root of pq over n. One mean, or z, is SRS, 10% condition, data is known, normal population, or n is greater than 30. We're going to use x bar plus or minus z star times standard deviation over square root of n. For one mean, or t, we're going to check SRS, 10% condition, standard deviation is not known. That's the reason that we're using t instead of z. Normal population or conditions for small, medium, and large samples are met. Therefore, we can use x bar plus or minus t star times s standard deviation for x over square root of n. For matched pair differences in population means, checking samples are matched, the list of differences is normal, or conditions for small, medium, and large samples are met. And we're going to use this formula, x bar sub d plus or minus t star times standard deviation of x d over square root of n. Differences in two population proportions, checking independent samples, both SRS, checking NP and Q for both samples greater than 10, 10% condition for both. We're using p hat 1 minus p hat 2 plus or minus z star times square root of this whole bunch of things. Differences in two population means, or t, independent samples, both SRS, both standard deviations are not known, both populations are normal, or both satisfy conditions for small, medium, and large samples. We're going to use this equation. So notice it's pretty similar with the formula above, except we switch from z to t. Degrees of freedom should use the calculator to figure that out. For t interval, the slope of a regression line, residual plot does not show any pattern or fanning. Residual histogram or box plot shows little skewness and no outliers. Therefore, we are allowed to use t equal to b minus, this should be the null hypothesis, but most of the cases it will be 0, so it doesn't really matter. Over standard error of b, notice have to write degrees of freedom equal to n minus 2. And talking about that, let me see. I know this is gonna be pretty useful if I just kind of go over them pretty quick. Sorry for kind of missing the first 2 rows, but I would just say it aloud to you guys. For one sample z-test for means, we're gonna check assumptions for SRS, 10% condition, data, standard deviation is known, normal population or n greater than 30. Null hypothesis will be mu equal to mu 0. Test statistic will be z equal to x bar minus mu sub 0 over standard deviation over square root of n. And for 2 sample z-test for means is independent samples, both SRS, 10% condition for both standard deviations are known, both populations are normal, or both n's greater than 30. Null hypothesis will be mu1 minus mu2 equal to 0. Test statistic will be z equal to x bar 1 minus x bar 2, quantity minus mu1 minus mu2 over square root of standard deviation of sample 1 squared over n1 plus standard deviation for 2 squared over n2. Okay, so that's the missing 2 rows. Yeah, and all of those stuff, you can feel free to like take a screenshot or copy them down. I won't read all of those since I think like a lot of them share similarities, but a lot of them do have little nuances have to pay attention. But it really depends on the questions. So yeah, that's all for hypothesis test. And just reinforce the 4 steps in any test. First, parameter, hypothesis or name. Second, assumptions or conditions. Third, picture, test statistic, p-value or degrees of freedom. Fourth, conclusion, have to be in context. That's why I bolded and capitalized it. Okay. And here is just a little review for when to like type 1 and type 2 error, and when to reject or when to accept. So when no hypothesis is true, but we reject no hypothesis, we have type 1 error, which is alpha. When we fail to reject no hypothesis, but in reality that no hypothesis is true, then we're fine, we're making a good decision. If we reject no hypothesis, in reality no hypothesis is false, then it's also a good decision. In reality, that's a power. Power just means we successfully reject the wrong no hypothesis. But if we fail to reject no hypothesis, knowing no hypothesis is false, then we made a type 2 error, which is beta. So yeah. Yeah. And it's really hard to say like which one is more meaningful or which one is more which one is more harmful or something. Like it really depends on your question. So if your question is like anyway, like if your question says like a guilty man, will he be sent to the jail or will he let it go to the world? It's it would definitely be harder. It would definitely actually be more harmful for let him to go to normal life, right? So that's the situation when you fail to reject the no hypothesis, but no hypothesis false. So our no hypothesis in that case will be assuming that he is innocent, which in reality he is not. But we still fail to reject no hypothesis, so we let him go. So maybe he will do something even harsher than what he already did. So it really depends on the question, right? So I can't really give you a exact conclusion for alpha or beta, which one is more powerful. Yeah, just pay close attention to the questions. And talking about that, that's all for this video, and this is our sixth review session for Inference. And yeah, that's all for it. Thank you so much for watching, and for the people that following along for all of my review sessions, thank you so much. Please feel free to leave any questions down in comments.